Okay, what we're going to do next is look at how molecular orbital theory would treat the picture of a pi bond. So how does molecular orbital theory explain the bonding in a pi bond? So we're going to use ethylene as our example because we used it when we talked about valence bond theory. And so let's remember our starting point for assessing the orbitals needed for molecular orbital theory so that we can make the new molecular orbitals is valence bond theory. So in valence bond theory would tell us that that carbon-carbon pi bond is formed by overlapping p orbitals. So remember, that's always the case. Anytime you have a pi bond in organic chemistry, valence bond theory will tell you that it's overlapping p orbitals, one on each atom involved in the bond, that's forming that bond. Okay? So that's our starting point. Now, if we were to extend this to molecular orbital theory would tell us that what we're doing is combining those same p orbitals in phase and out of phase. All right, let's take a look at the structure of ethylene. So the first thing we're going to do is the same thing that we did when we looked at ethylene in the context of valence bond theory, and that's to make a list of all the bonds that we have. So we have 4 carbon-hydrogen sigma bonds, and we have a carbon-carbon sigma bond, and we have a carbon-carbon pi bond. Every bond in an organic molecule is going to be associated with a bonding orbital and an antibonding orbital. So what this means is the following. Let's start with the easiest one, the carbon-carbon sigma. I'm saying that's the easiest one because we only have one of those, and it's going to be fairly straightforward. So if we have a carbon-carbon sigma bond in the molecule, what that means is that we have a carbon-carbon sigma bonding orbital and a carbon-carbon sigma star. So again, for every bond that you have in an organic molecule, whether it's a sigma or a pi, you'll have a bonding orbital and an antibonding orbital. Okay, now let's look at the CH sigma. Well, we have 4 of those bonds, 4 CH sigma bonds, which means that we're going to have 4 CH sigma orbitals, and consequently, 4 CH sigma star orbitals. And then finally, for the pi bond, we're going to have a pi bonding orbital and a CC pi star antibonding orbital. So the set that we just drew out, all of these are the molecular orbitals in ethylene. So we just made a list of all the molecular orbitals that are present in ethylene. So these are the MOs in ethylene. Okay, if we were to construct a molecular orbital diagram, so much like we've been doing for H2 and H2 plus and HE2, if we were to construct a diagram like that, there would be a lot of orbitals involved. So we'd have all of the hydrogen orbitals and then all the orbitals on the carbons, and all of these would be mixing, in phase, out of phase. Point being, you'd have a very complicated diagram or a relatively complicated diagram. So instead what we're going to do is we're just going to pull out a piece of the whole diagram, and that's the pi component. And we're just going to draw that, recognizing that this is just going to be a part of a larger, more complicated diagram. So each of the carbons is using a p orbital to participate in that pi bond, and each of those p orbitals has a single electron in it. The 2 p orbitals are going to mix in phase to give us a bonding result, and out of phase to give us an antibonding result. The in-phase combination, which is the bonding combination, is a pi orbital, because we're dealing with a pi bond. And the out-of-phase combination, which is the anti-bonding orbital, is the pi star. So we have pi and pi star. Now the electrons that came in with the p orbitals, again, remember, we're going to put those into their new home in the bonding orbital. So electrons are lower in energy when they're in bonds than when they're not in bonds. Okay, now let's look at pictures of these orbitals. So starting with the bond axis, there's a couple of ways you can draw the bonding orbital, the pi bonding orbital. So you can draw two p orbitals really close to each other like this. I'm going to make the nuclei a different color. So here are the nuclei, these little red dots. And so what you would do is bring two p orbitals next to each other so that the phases that are the same are right next to each other. So the shaded phases are right next to each other and the unshaded phases are right next to each other. That would be an in-phase combination. Or you can draw it like this. So again, we have the bond axis. We have our nuclei. And then we have a region up here that's in one phase, and a region down here that's in another phase. Now remember that, just like in a regular p orbital, there's a nodal plane that coincides with the bond axis. So this is a nodal plane. So that's the bonding orbital, the pi bonding orbital. Now the anti-bonding orbital would look like the following. So here are our nuclei. And so this time when you combine the p orbitals, I need to move over that nucleus. This time when you combine the p orbitals, you're combining them in such a way that opposite phases are next to each other, like so. So that gives us the nodal plane that we had in the original, the pi orbital down below, but it also gives us a nodal plane here that's perpendicular. Both of these planes are perpendicular to the plane in which the orbital is drawn, or the plane of the paper. So you have two nodal planes. And here are the bond axes. So that's what a pi and a pi star orbital would look like. Now, in general, when we think about the molecular orbitals in an organic molecule, there's going to be a particular set of molecular orbitals that every molecule will have. The general rule of thumb for the order in which they appear, their order of their energies, is the following. The lowest energy is sigma, followed by pi, then any non-bonding orbitals you may have. So remember, N stands for non-bonding. Then pi star, and then finally the highest energy molecular orbitals will be sigma star. So sigma is the lowest, then pi, then non-bonding, then pi star, then sigma star. So that's a good rule of thumb for when you're thinking about reactions. Okay, so we've drawn a few simple molecular orbital diagrams, and honestly, that's really all you need to be able to do. But we're also going to draw one that's a little more complicated. And the reason for that is so we can look at a particular type of orbital that we haven't seen yet. That would be the non-bonding orbital, so we want an example that has one of those. And then introduce some other terminology that relates to molecular orbitals. So we're going to draw a molecular orbital diagram for what we're going to call pyramidal ammonia. So ammonia is NH3. So here's a Lewis structure for it. We're specifying pyramidal so that we know what the geometry is, and that in turn is going to tell us which orbitals to use. Now, pyramidal in this context is referring to the molecular geometry. The molecular geometry is the shape that we get when we're only looking at the atoms. By contrast, something called the electronic geometry would be us also including the lone pairs and unpaired electrons. So that the electronic geometry would be described by the positions of the atoms and any non-bonding electrons. So once again, our starting point for constructing molecular orbitals is to think about valence bond theory. So valence bond theory is going to tell us that each of the nitrogen-hydrogen sigma bonds is formed by the overlap of an s orbital on hydrogen and an sp3 orbital on nitrogen. Valence bond theory would also tell us that the nitrogen lone pair, remember the lone pairs are contained in hybrid orbitals. So the lone pair, because the hybridization of the nitrogen is sp3, the lone pair is in an sp3 orbital. Okay, so let's draw a diagram. So we'll have energy increasing from bottom to top. And we've got a bunch of different atoms involved here. We have 3 hydrogens. So let's put those over here. And each of those is using a 1s orbital to contain a single electron. That electron is messed up. I'm going to redraw it. There, that's the nicest electron of the 3 now. Okay, so there are the hydrogens. The nitrogen orbitals we're going to put on the right side. Now it's sp3 hybridized. So remember, it's only the valence orbitals that we need to worry about because it's the valence electrons that are involved in making bonds. So the nitrogen orbitals are going to be over here. And these are all sp3. The orbitals on the nitrogen are going to be at a lower energy than the orbitals on the hydrogen, and that's because nitrogen is more electronegative than hydrogen. Nitrogen has 5 valence electrons. So let's put 5 electrons into its valence shell, and I'm going to add the last one in over here in the sp3 orbital on the far right. Okay, so the first thing we want to do is make combinations of orbitals, one on hydrogen and one on nitrogen, and combine those in phase and out of phase to get each of the nitrogen-hydrogen sigma bonds. So let's start out and do that. So we can make an in-phase combination between this 1s orbital and this sp3 orbital. And we can make an out-of-phase combination using the same 2 orbitals. So that takes care of one of the 1s's and one of the sp3's. Now I'll repeat that for the next sp3 s combination. So we first envision the in-phase combination of those 2 orbitals, and then the out-of-phase combination. Of the same 2 orbitals. And finally, there's a third NH sigma bond, and so we have to take the remaining s orbital on the third hydrogen and combine that both in and out of phase with a third sp3 orbital, like so. The in-phase combination results are all going to be NH sigma orbitals. These are all bonding orbitals. And the out-of-phase combination results are all going to be NH sigma star, which are all antibonding orbitals. Now you might notice that this orbital right over here that I've just circled, we have not done anything with. We didn't mix it with any other orbital. It's just hanging out. And so what we're going to do with it is the following. We're going to bring it into the middle of the diagram at exactly the same energy level, and we're going to give it a different name. We're going to rename it as a non-bonding molecular orbital. So remember, the orbitals in the middle of the diagram are the molecular orbitals. The ones on the outsides, on the sides of the diagram, are the atomic orbitals that we use to create them. So all we've done with that last sp3 orbital is just give it a new name. It looks exactly the same as it did when it was an sp3 orbital. It just has a new name. Okay, so now we have a set of electrons that came in with the atomic orbitals, and we need to put those in to our new molecular orbitals. So there's 3 from the hydrogens and 5 from the nitrogen for a total of 8 electrons. So using Aufbau, Pauli exclusion principle, and Hund's rule, we would start at the bottom. So our lowest energy molecular orbital is an NH sigma. So we'll put 1 electron there. But this is a set of degenerate orbitals. All 3 NH sigma orbitals have the same energy, which means you can think of them as being a subshell, which means that the next electron goes into the second NH sigma, and the third electron goes into the third NH sigma. Now that each of the orbitals in that subshell is singly occupied, that is to say, has 1 electron in it, we can go back and start pairing up. So that takes care of 6 electrons, but we need 8. We have a total of 8 that we have to put into the molecular orbitals. So the remaining 2 end up in the non-bonding orbital. Okay, so what can we get from this? Well, one of the things that we're going to get out of this is this idea of the frontier orbitals. Now, the frontier orbitals are the ones that are involved in a chemical reaction. And the guy who came up with this was this guy named Kenichi Fukui, and he got the Nobel Prize in 1981 for figuring this out and coming up with this theory. So what this is based on is the idea that each of the partners in a typical chemical reaction, let's say you have 2 chemicals reacting with each other. Each of those chemical partners is going to use one of its orbitals to interact with the other partner. Those are going to be called the frontier orbitals. Okay, so let's say that we have 2 chemicals that are reacting or interacting in some way. In such a case, typically what's happening is the following. One of them supplies the electrons to make a bond to the other one. So one is supplying the electrons, and the other one accepts those electrons. All in the service of forming a bond between those 2 chemicals. The one that's supplying the electrons can have different labels, as we'll see throughout the course. The 2 labels that it can either be acting as what's called a nucleophile, or it can be acting as a base. Now, when we say base in this case, we mean Bronsted base, so something that's accepting a proton. The thing that's accepting the electrons we're going to call an electrophile, or depending on who it's accepting electrons from, we may call it an acid. Now the differentiation between those terms, so what's a nucleophile versus a base, and what's an electrophile versus an acid. We're going to get into all of those details as we go forward. But for now, just think of it this way, that the thing that's supplying electrons to something else, the label it's going to have will be either as a nucleophile or as a base, and something that's accepting electron density from something else will be called either an electrophile or an acid. Okay, so let's take a look at the molecular orbital diagram that we just made on the previous page. Gee, if I had known this, we wouldn't have had to draw all that diagram out. Haha, just kidding. All right, so here's the same diagram. Now remember, the molecular orbitals are these guys right here, the ones in the middle of the diagram. Let's make this better, okay? Like so. All right, so let's say that you are an ammonia and you're going to react with some other chemical. And in that reaction, you're going to be the one supplying the electrons to the other chemical to form a bond to it. Okay, so if you're the one supplying your electrons, this is going to track with what you know about how atoms use their valence electrons to form bonds. So they use their outermost electrons, the ones that are least tightly held by their nucleus, to form a bond to some other atom. The same is true if you have a molecule that's interacting with a different molecule. It's going to use the highest energy electrons that it has to do that. In terms of molecular orbital theory, we can put labels on some of the orbitals in a molecular orbital diagram. The electrons that are the highest energy electrons in any molecular orbital occupy what's called the highest energy occupied molecular orbital, or the HOMO. In ammonia, the highest energy molecular orbital that contains electrons in it is the non-bonding orbital. So we're going to say in ammonia, the HOMO is the NMO. So that's the highest occupied molecular orbital. So if an ammonia comes up to somebody else and wants to react with it, those are the electrons it's going to use, would be the non-bonding electrons. It's going to use those to participate in a reaction with somebody else. Now the somebody else that's accepting the electrons is going to have an empty slot, an empty orbital, to accept those electrons into. Now if you're accepting electrons, you're going to try to put them into the lowest available empty slot you can. Now if it's ammonia that's doing this, its lowest available energy empty slot would be the NH sigma star. Now that could be kind of confusing because those are the highest energy orbitals in the whole diagram. But in terms of the molecular orbitals, they're the lowest energy ones that you have that you can accept new electrons into. Such an orbital is called the LUMO, the lowest unoccupied molecular orbital. And so in NH3, the LUMO is any of the NH sigma star orbitals. Okay, so let's go back up to the top of the page and fill in more information. The one that's supplying electrons in a reaction, the chemical that's supplying electrons, we'll either call a nucleophile or a base, depending on exactly what it's doing, and it will be using its HOMO, its highest occupied molecular orbital. Its partner, the one that's accepting the electrons from it, we're either going to call an electrophile or an acid, depending on exactly what it is doing in the reaction. But either way, it's going to use its LUMO, or its lowest unoccupied molecular orbital. So you don't need to know how to construct a diagram that's this complicated. I'm probably not going to ask you to do that. But I will ask you to interpret things. So to look at a diagram like this one and to be able to pick out the HOMO and the LUMO, for example, that would be something that you should be able to do. But what we're going to be doing with this is looking at some chemical reactions next and learning how to assess, using some certain pictures that I'm going to show you, what the HOMO and the LUMO in the reaction are.